Alright, let's go ahead and write down a review here of the big ideas that we saw on Monday. Okay, so we've been looking at functions or mappings, sometimes we call them. So a function from a set A to a set B. We know that in this notation, A is the domain and B is what we call, of course, the codomain. So this function is, of course, one-to-one, if it satisfies the following property. If someone out there tells you that f of x is equal to f of y, yeah, and you can conclude that x must be equal to y. So the only way for this to happen is if x is equal to y, then this function is said to be one-to-one. Yeah, and the function, again mapping A to B, is onto if the image of f is the entire codomain. The image of f is equal to the codomain B. Alright. Now, if it turns out to be the case that a function is both one-to-one and onto, then we call it a bijection. So if a function, again mapping A to B, is one-to-one and onto, we call it a bijection. Whoops. Yeah, so here my function is one-to-one and onto. In this case, we say f is a bijection. F is called a bijection. Yeah. And the inverse of a function exists if and only if f is a bijection. So f going from A to B has an inverse if and only if f is a bijection. F is a bijection. Okay. Alright, so that's sort of what we started talking about clear back on Monday. Yeah, just on Monday. Alright, so what are we going to do today? We actually have a lot to do today. We'll see how long this video gets. I don't want to make it too long, but we'll see how we do here. Okay, so what I want to do is actually prove that f is invertible if and only if f is a bijection. So let's actually prove that fact. So f inverse exists here. F inverse exists if and only if f is of course, what we call a bijection. Yep. So f inverse exists if and only if f is injective and surjective. Okay, now then we're going to start something new and very interesting, I think. We're going to start talking about countability. But before we get to that, we need to start talking about finite and also infinite sets. Infinite sets. Okay. Now, in order to talk about finite infinite sets, you do have to view them, you have to view sets as corresponding to the domain perhaps of a bijection, or something along those lines. So the point of introducing bijections, one of the main benefits of doing that is that we're going to be able to talk about finite and infinite sets. Okay, now thirdly, we're going to start talking about countably infinite and uncountably infinite. So countably infinite, countably infinite versus uncountably infinite. Uncountably infinite. Okay. All right. So, what do we want to do first? First, we want to go ahead and prove this theorem that f inverse exists if and only if f is a bijection. All right. So let's go ahead and call this a theorem. Okay. Okay. So what I'm going to do is define a function f, and it is going to map a domain A to a codomain B. So let f inverse going from A to B be any function. It's any function in the world. Okay. Now, of course, the statement is that f inverse exists if and only if f is a bijection. Okay. All right, so this is an if and only if statement, so of course I have to sort of prove the theorem in both directions. Yeah, and that's what we're going to try to do here. So here's our proof. Okay, so let's prove this direction first. Okay, right. So when I'm proving this direction, I'm going to be assuming that F inverse exists. I want to somehow, from that, conclude that F must be a bijection. So assume F inverse exists. Okay. My goal is to prove that F is a bijection. Okay. So first I want to prove that F is 1 to 1. Okay. Now to prove F is 1 to 1, all I need to do is suppose that F of X is equal to F of Y. Right? And I want to somehow conclude that X must be equal to Y. So if F of X is equal to F of Y, what I can do is just apply both sides to the inverse function of F. So if F of X is equal to F of Y, then that tells me that F inverse of both sides must be equal. Right? But F inverse of F of X is just X, and F inverse of F of Y is just Y. So I started off with the assumption that F of X is equal to F of Y. I concluded that X had to be Y. Therefore, F is 1 to 1. Or if you like, F is injective. F is 1 to 1. And sometimes, of course, we call this injective. Okay. So that proves that I am injective. But I want to suppose, I want to prove that F is a bijection. So I have to prove that it's onto. Okay. So I have to prove that the image of F is all of B. Okay. I want to show that the image of F is all of B. So now we must show that the image of F is equal to all of B. Okay. Now, when we're proving a set equality, because here we want to prove an equality of sets, you always should be sort of going back to fundamentals and asking yourself what this means. It means that the image of F is contained in B, and also B is contained in the image of F. Okay. Now one of these is clear. The image of F is always going to be contained in B, just by construction, just because I know this is a function and the codomain is B. So the image of F in general always lies in the codomain. So this is true trivially. Yeah? This is trivially true. Trivially true. Okay. The one that we have to work a little bit for is to prove that the codomain is contained in the image. So we want to prove that B is contained in the image of F. Okay. So what I need to do is the following. Okay. What I can do is the following. In order to prove this, I need to assume that I'm given an element inside of capital B. So let little b be in capital B. What I can do is actually define, let's say, little a to be F inverse of B. Yeah? Then look what happens if you apply F to A. Then F of A is equal to B. Right? So therefore B is contained in the image of F because I've written it as F of something coming from A, capital A. Right? So that actually proves this containment also. Right? So this shows that F is onto. Therefore, F is onto. Or if you like, F is surjective. If you like some other words, some other terminology. Yeah? So that proves that F is a bijection because I proved it is 1 to 1 and onto. Okay. So that proves the forward direction in the proof. So I need to prove the reverse direction. Okay, well, let me scroll down here. Okay, so let's scroll down and let's prove the reverse direction. So now I want to prove this direction. So now what I'm going to assume is that F is a bijection. And I want to be able to show that F must have an inverse. So assume F is a bijection. Is a bijection. Okay. Now, F is a bijection, so what I can do is this. I can say given any element B living inside of capital B, we know there is some little a living in capital A such that f of A is equal to little b. Why do we know this? Well, we know this because f is on 2 because it's a bijection. Yeah, f is on 2. So everything in B can be written as f of something coming from A. F is on 2. Okay, so for each little b coming from capital B, what I'm going to do is define a function as follows here. So define g evaluated at B to be A. So this defines a function going from capital B to A. And since f is on 2, I know that the domain of G is actually all of B. So this defines a function, which we're calling G, that maps capital B to A. Okay. Now, one thing that I do need to note here is that this is a function. And the fact that this is a function follows from the fact that f is 1 to 1. So this is a function since f is 1 to 1. Now you might ask yourself is, how does f being 1 to 1 imply that g is a function? See, what you're worried about happening is something like this. So you're worried that maybe f evaluated at 1 is equal to f evaluated at 2 is equal to b. In which case, g of b is simultaneously 1 or g of b is equal to 2, right? In which case, g is not actually a function because you do not have a unique output corresponding to the input of b. So that does not happen precisely because f is 1 to 1. All right. And it turns out that g is the inverse function of f. Yeah. So that's the key takeaway. G is the inverse function of f. Inverse function of f. Okay. And that actually completes the proof. So we've just shown that a function is invertible if and only if that function is a bijection, if it's both 1 to 1 and on 2. Okay, let's actually move on and start talking about finite sets and infinite sets. Okay, so what I'm going to do is give you a set. We're going to call this set alphabet. Alphabet. Okay, so alphabet is the set consisting of the 26 letters in the standard English alphabet. So A, B, C, and then I skip a few, I put my ellipses, and I end with maybe X, Y, and Z. X, Y, and Z. Okay. Now, this is an example of a finite set. Yeah. Now, one way to describe that is precisely because there is a way to map this set to the set 1 through 26, right? So there exists a bijection. There exists a bijection. Let's call this bijection F. F, the domain of this bijection is going to be alphabet. And it's going to map it to the set 1, 2, 3, all the way until I get to 24, 25, 26. Yeah? And the way I can define this function is, well, it's, there's multiple ways to define it, but a natural way is to say f of capital A is 1, f of capital B is 2, and you go on in this fashion, etc., 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 until you get maybe f of y is equal to 25, and then f evaluated at z is equal to 26. 26. Yep. So because this bijection exists, we say that this set is a finite set. Okay. So let's make a definition here. Definition. And that is that of what it means for a set to be a finite set. So X is finite if there is a bijection. And, X here is a set, so I should have wrote that down, but X is a set, and we say it's finite if there is a bijection, F, that goes from X to some set of the form 1, 2, all the way up to N. Yeah. In which case, X has N elements. Yeah. So we say that the cardinality of X is N. So we say that the cardinality of the set X is the positive integer N. Okay. So let's do an example here. We'll look at a quick example. What's a good example? Let me think. Okay, yeah. So let X be equal to, let's see, Jokic, Barton, Porter Jr. Skip this over here a little bit. And then we have Murray. And we have Gordon. Okay, so this set X is actually the set of starters for the Denver Nuggets. Yeah, we have 5 stars. We have the center, shooting guard, small forward, power forward, and what am I missing? Point guard. Yeah. So these are the starters for the Denver Nuggets, and this set has a cardinality of 5. Yeah. This set has a cardinality of 5. And that is because there is a bijection. There is a bijection. F that takes X and it maps it bijectively to the set 1, 2, 3, 4, 5. Yep. And one thing to keep in mind here is that there's actually many bijections that you could actually write down. In fact, it's sort of interesting to sort of think about how many bijections are there between X and the set 1, 2, 3, 4, 5. Yeah? So think about that. Think about how many bijections there actually are here. In fact, I'll make that an extra credit question. Yeah. Let's think about that. Yeah, so here's extra credit. Yeah. So all you have to do is email me your response and do so in a timely manner. So let's try to get this in before maybe Friday morning. I think that's probably a good cutoff time. So here's the extra credit question. So how many bijections are there in this specific example? Yeah. Now, just keep in mind that in the definition of cardinality and finiteness of a set, you just need the existence of a bijection. It doesn't say anything about the existence of a unique bijection, because here there is, if I give you a bijection, someone else might give me a completely different bijection. So I want to ask how many bijections are there in this specific example. Okay. So just email me your response to that by Friday morning. Okay. Ah, yes. Okay. So we saw an example of a nice finite set. We understand what a finite set means. It just means mathematically that there's a bijection between your set and a set of the form 1, 2, 3, 4, 5, 6, 7, 8, etc., all the way up until you reach some finite integer n. Okay, yeah. And in this example, n is equal to 5, of course. Okay. So now let's talk about what an infinite set is. Okay. So this is another definition. So infinite means not finite, right? So not finite means that there is no such bijection. Okay. So x is said to be infinite. And here again, I messed up saying that let x be a set. X is infinite if there is no bijection. So there does not exist any bijection. F going from x to a set of the form 1, 2, 3 all the way up to n. And this is for any n. So no matter how you choose n, if you cannot find such a bijection, then x is infinite. And mathematically, you're just saying x is infinite if it is not finite. And this is the definition of being finite. Okay. So, we've seen a number of infinite sets, believe it or not. So let's write down some examples. Whoa, I gotta switch colors here. Otherwise, everybody will be confused, including myself. So, example. I will say examples. Okay, let's look at one example is the set of positive counting numbers. 1, 2, 3, etc., etc., etc. Yeah? This is an example of an infinite set. Why? Because I cannot construct a bijection going from the set of natural numbers to a set of the form 1, 2, 3, 4, all the way up until you get to some finite integer n. I cannot possibly construct such a bijection. Now, you might want to ask yourself, well, why cannot you construct it? So try to actually show that. Try to show that you cannot construct this bijection. Now, to do that, you simply assume that you can, and then you arrive at some contradiction. Yeah. So I encourage people to try to think about how they would show that too. Okay. Another nice example is a set of integers. The set of integers, remember, is a set of positive, so it's a set of naturals. I throw in 0 and then I put the negative naturals. Yeah. Okay. So it's the naturals, the negative naturals, and then together with 0. All right. Now 3 is of course the set of rationals. Now the set of rationals we know we can write in the form p divided by q, with the property that p is an integer and the denominator q is a natural. Yeah, that's one way to sort of describe the field of rationals. Remember, because this is a field. Okay. 4. You go one step higher, you can look at R. Yeah. Now, of course, R is somewhat difficult to construct, but essentially what you're doing is you're taking Q and you're filling all the holes in. Because Q has little pieces missing, you just kind of stick some what's that stuff called? Epoxy or some Bondo. You put it over and you get R. Okay. Now we can look at several other examples. We've looked at several examples of infinite sets. R2, R3, the field of complex numbers, the vector space of all 2×3 matrices, the space of all polynomials of degree no more than 13 with real coefficients. Yeah, etc. These are all examples of infinite sets. So everything we've written down here is an example of an infinite set. However, and interestingly, and the next topic that we're going to talk about is a sort of notion of being countably versus uncountably infinite. Okay, so you see that there's actually two different types of infinities. So everything below this line is what we call uncountably infinite. Everything above this line is an example of something that's countably infinite. They're both infinite, but one in some sense is more infinite. Yeah? So in some sense, these sets here are more infinite. They're more infinite. More infinite. More infinite. Okay, so let's go ahead and give maybe another sort of heuristic description of this. Actually, let me go ahead and clear this. Okay. So an example of a set that is countably infinite is the set of naturals. Okay, so over here I'm going to put the set of naturals here. Naturals. Yeah? Versus the set of real numbers. Right? Now, n being infinite this is sort of like you're in a discrete realm. You're infinite, but you're discrete, right? In the sense that you have sort of little atoms living here. You have infinitely many atoms. Yeah. So here you have like you have an atom at 0. So let's just label this. You have 0, 1. Wait. 1 is not included in the natural. Sorry. Don't tell me when I wrote that. This is 1, 2, 3, 4, 5, 6. And of course you go on for infinity. Off to infinity. So of course I can't draw infinitely many dots here. So I'm putting my ellipses. Yeah? Okay. The point is that you're infinite, but you're discrete. Now, when you move to the set of real numbers, you are infinite, but there's like a continuum of real numbers, right? That's why we say you draw the real number line. We draw a line, we draw a continuous line. Yeah? And this is like a continuum or a continuous. Well, we'll say continuum because it's a fancier word. Continuum. Okay. So in jumping from the set of naturals to the set of real numbers, you're going from being countably infinite to uncountably infinite. Okay. So let's just write that out. So this is an example of a set that's countably infinite, versus a set that's uncountably infinite. Okay. Now, let's see. Okay, so I'm going to, we'll get back to this here in just a second. Well, at the end of this video, I'm going to get back to this picture. Ooh, okay, since I want to come back to this picture, I'm gonna leave it open here. So let's see if my poor whiteboard can handle it. Because, my whiteboard's like really laggy all the time. Okay. So with that in mind, we can actually go ahead and try making a definition of what it means for a set to be countably infinite. So this time I will sort of make a proper definition. Okay, so I'm going to take X to be a set. So let X be a set. Okay. X is countably infinite. If there exists a bijection that takes X and it maps it to the set of natural numbers. Okay, X is a set, X is countably infinite if you can find a bijection that takes X to the set of natural numbers. Okay, let's look at a super awesome example. Example here. Let's do an example in yellow here. I'm going to write down an example. Okay. Let's go ahead and let X be the set of integers. Okay? So X is my set of integers. All right. Let's try to find a bijection from X to the set of naturals. Yeah? Let's show that Z is countably infinite. Or sometimes people just say countable. Instead of saying countably infinite, people just might say Z is countable. Or likewise, R is uncountable. All right. But in this example, let's show Z, the set of integers, is countable. All right? So what I need to do is find a bijection from Z to the naturals. Now this actually is pretty cool when you think about it here. All right, so what I'm going to do is, what am I going to do? Aha, yes. So I am going to write down the set of integers here. Now, of course, I can't write them all down because there's infinitely many, but I can sort of get a grasp of what's going on. So I have 0, 1, then I have 2, and then I have 3, and then I go off to infinity, And then I have, of course, negative 1. Whoa, I'm messing up here. We're going to put negative 1 right here, negative 2, and then we'll put negative 3. Okay. So what I'm going to do is just start counting off, and then of course this goes off to negative infinity. I'm going to start counting off. So I want to map this to the set of naturals. Natural starts with 1. So I'm going to say that f of 0 is 1, and then f of 1 is 2, and then 3, and then 4, and then 5, and then 6, and then 7. See? So I just kind of go back and forth like a pendulum. 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., etc. Okay. So what I can actually do now is try to come up with the function. right? So the function that I've defined, let's just write down some of the values. F of 0 was 1. F of 1 was 2. F of negative 1 was 3. F of 2 was wait a second. I'm confused now. Yeah, F of 2 is 4, etc., etc. Right? And let me just go ahead and be precise here. I'll write the rest of them down. So F of 2 was 4. F evaluated at what do I need next? Negative 2 is equal to 5. F of 3 is equal to 6. F of negative 3 is equal to 7, so on and so forth. Okay, so what you can do is try to give a general formula for the function. Let's try to do that here. Okay, let's do it in yellow. Okay, so f of x. How do I define f of x? Now it is going to sort of depend on whether x is negative or positive, etc. But you see, if x is positive, then you're just multiplying. You're just taking twice x, unless you're at 0. Unless at 0. So f of x is equal to let's see. I'll probably be able to include that inside of the case when x is negative. Let's see. Okay, but if x is strictly positive, I just take 2x. So this is when x is an integer and it's greater than or equal to 1. So if x is greater than or equal to 1, then I just the output of this function is 2x. Yeah. Now let's look to see what happens if x is less than or equal to 0. Yeah. If x is less than or equal to 0. And that's gonna take care of all cases, yeah, because this is gonna be a function from the set of integers to the set of naturals, yeah. So this function f is mapping the integers to the naturals. Okay. Now it's a little bit trickier to determine what this function is doing at the negative values, but let's try to figure this out. So if x is, for example, negative 1, what I did is I multiplied by 3. All right. But then if x was negative 2, I multiplied by, okay, I see the pattern now. You take twice negative x, so I do negative 2x and then I add 1, I believe. Or do I subtract 1? Yeah, I add 1. There we go. Yeah, okay. Now this works when x is 0, because if x is 0, then I get 1. Okay, so this is my bijection. Okay, so we just proved that the set of integers is countably infinite because we found an explicit bijection that took me from the integers to the naturals. Nice, nice, nice. Okay. So another sort of another interesting question here. So how can we show that the set of rationals here is countably infinite? Because it is. Believe it or not, the set of rationals is countably infinite. Yeah. And the question is, how do we show that? Okay, so let's actually move to that now. I'm going to show you why the set of rationals, or the field of rationals, if you like, is countably infinite. Let's go ahead and clear the canvas here. Okay, so we're going to go ahead and make a proposition here. Alright, so this is a proposition. Okay, so I'm going to propose that Q is countably infinite. So the set of rationals is countably infinite. Countably infinite. Okay, so the way we're going to actually prove this is as follows. What we want to remark is that it suffices to show that a different set is countably infinite. So we're going to take Q with a superscript plus. This is just going to be the set of all positive rationals. So it's going to be the set of all x's that are rational with the property that x is strictly larger than 0. Yeah. is countably infinite. Countably infinite. And then I could use sort of the same argument that I used in proving that the integers were countably infinite, where we just sort of counted back and forth. We kind of just said, okay, I'm going to count first, starting with the positive integers, and then I just kind of bounce back and forth and count that way. Okay. So we're going to show that the set of positive rationals is countably infinite. Now, the way we're going to do that is sort of just set up a table here. Okay. So let's write down a table. Now, this table is going to contain all possible rational numbers. So I'm going to start with 1, 1, and then 1/2, and then 1/3, then 1/4. Whoops, let's see. 1 second here. Yeah, 1/4. Yeah. And then I go off for my ellipses. And then in the second row, I'm going to put 2 over 1, and then 2 over 2, and then 2 over 3, and then 2 over 4. And I'll put my ellipses. Then in the third row, I'll put, you guessed it, 3 over 1, 3 over 2, 3 over 3, 3 over 4. I put my ellipses. And then in the fourth row, I'll put 4 over 1, 4 over 2, 4 over 3, 4 over 4, and I put my ellipses, yeah? And then I have to put ellipses vertically because, this is going to be an infinite array, and, well, I can't quite write an infinite array down. So I put my ellipses, yeah? Okay, so this is an infinite array, and it contains every single positive rational number. Now what I'm going to do is start counting. So I start by, let's see here. Let's start with 1 over 1. So I'm going to start there. I jumped to 2 over 1. Then I go to 1/2. Then I go to 1/3. And then in this pattern, I would go to 2 over 2. However, 2 over 2 is really 1 over 1, and it's already on my list. So I skip 2 over 2, and I go directly to 3 over 1. Yeah, so here I'm literally just skipping 2 over 2 because it's already on my list. I don't need that. So I skip from 1/3 all the way to 3 over 1. And then I go down following this pattern to 4 over 1. Then I go to 3/2, and then I go to 2/3, and then I go to 1/4. And then I would go over here to 1/5. So this is me going over to 1/5. Then I would go back down to 2 over 4. But 2 over 4 is already on the list. Yeah, so I don't want 2 over 4. So after I've hit 1/5, I skip 2 over 4 and I go to 3 over 3. But 3 over 3 is 1 over 1. This is also on my list. So I'm skipping 3/3. Yeah. So I'm skipping 2/4, 3/3. Then I go to 4/2. 4/2 is 2. 2 over 1 is already on my list. So I'm skipping 4/2 also. Now what I would be doing, had I written down what this ellipses represents, that I'd be going to 5 over 1. Right? So then I'd be going to 5 over 1 here. Yeah? So you keep going on in this pattern, and this tells me that yes, I can in fact count all of the positive rationals. Now that's giving me a bijection from the positive rationals to the set of natural numbers. Yeah. And since I counted the positive rationals, it's possible to count the negative rationals, and then it's possible to count them together. And that gives me the fact that the field of rationals is countably infinite. So that's the proof here. Okay. Okay. So what we're going to do now is prove that the set of numbers in between 0 and 1 is actually not countably infinite. Okay, so this is a theorem. We're going to call this a theorem here. Okay, so this is our theorem here. Theorem. Okay. Okay, so the set. let's write this out here. So the set of real numbers in between 0 and 1. Yeah. Remember, this is the collection of real numbers R with the property that 0 is less than or equal to R is less than or equal to 1. Okay. So this set is not countably infinite. Is not countably infinite. Of course it is infinite, but it's not countably infinite. In other words, there is no bijection from this set to the set of natural numbers. Okay, so let's write down here a proof here of this fact. And this proof originally dates back to Cantor in 1891. Yeah, and this is called Cantor's diagonalization argument. Okay, so let's go ahead and suppose that the set is countably infinite. So suppose that this set is countably infinite, and we're going to arrive at some sort of contradiction. Okay, so I'm going to suppose that the set is countably infinite, i.e., there exists a bijection. What's typos here? Okay, so there exists a bijection. We'll call this bijection G. That goes from wait, 1 second here. Yeah. Okay, so according to our definition, there has to exist a bijection going from this set to the set of naturals. Okay. So because this bijection exists, I know that the inverse function exists. Yeah. Therefore, there exists an inverse function we'll call this inverse function f. Okay, so the inverse function is going from the naturals to 0, 1. And since f has an inverse, yeah, g and f are inverse function pairs. So I know, according to the theorem that we proved at the beginning of class, that f is also a bijection. Yeah? So we want to note that f is also a bijection. Note, f is also a bijection. Okay. So really, in assuming that 0, 1 is countably infinite, I'm getting a bijection from the naturals to the set 0, 1. Okay. Now, what I'm going to try to do is contradict the fact that this is a bijection. Because f being a bijection means it's 1 to 1 and onto. I'm going to try to produce a number inside of 0, 1 that is actually not in the image of f. In other words, I'm contradicting the fact that this is onto. Okay. So let's try to construct that number. Okay, so our goal here is to try to construct a number r living in this interval such that r is not in the image of f. So such that r is not contained in the image of f. Okay. And in doing so, this of course contradicts the fact that this is a bijection, because then my function is not onto if I'm able to construct such a number r. Okay. So how do we do that here? Let's put our little squiggle here. Okay. So the real number r, since it's living in the interval 0, 1, it's going to have a decimal representation, and that decimal representation is going to be something like 0, and then something in the tenths place, and then something in the hundredths place, etc. So 0, R1, R2, R3, and then of course R4, and then I go on forever and ever. And I'll put my ellipses here. Yep. Okay. So in order to specify R, I have to specify R sub j. Yeah, for each j bigger than or equal to 1. Yeah. And of course, these R sub j's are living in between 0 and 9. Yeah. So R sub j is living in between 0 and 9. So it's an element of the set 0 through 9. Let's write that out here. Whoops. Yeah, so these decimals, of course, live in the set 0, 1, all the way up to 9. Yeah, because this is the decimal representation that I'm trying to give for R. Okay, now the way I'm going to define it is as follows. So, okay, so f is a function from the set of naturals to the interval 0, 1. So f of n for each n has a decimal representation. Decimal representation. Okay, so keeping that in mind, what I'm going to do is define Rn as follows. So R sub a, or I'll just say R sub j here. Let's say R sub j. R sub j, the way I'm going to define R sub j is as follows. Okay. How are we going to do that? Well, my screen's kind of laggy right now. Okay, so R sub j is going to be defined as follows. So it's going to be 0 if the jth digit after the decimal in f sub j is equal to 1. So for example, let's suppose that, let's just do a quick example here. Okay, let's suppose f of 2 is equal to 0. Let's say 2, 1, 3. Yeah, something like that. Okay, because here j is equal to 2, and because the jth digit, in other words, the second digit after the decimal is a 1, I know that r sub 2 is going to be 0. Okay, so that's what this sort of formula is saying. Okay. Now, if this is not the case, we're going to put a 1. So in all other cases. In all other cases. Or I'll just put else here. Describe it here a little bit simpler. Else. Okay, so if the first condition isn't met, then I'm going to put a 1 in the jth digit. Okay. Now, it turns out that what you can show is that f of j, or we'll just say f of n here, f of n is not equal to r for any n inside of the domain of f. Yeah. So this implies that f is not on 2. F is not on 2. Yeah. So this contradicts the assumption that f was a bijection. Yeah. And so therefore, this completes the proof. Yeah. So the closed interval from 0 to 1 is not countably infinite. And, okay, so an immediate sort of corollary here is that the open interval from 0 to 1, right? So this is the set of all x's in R, of course with the property that 0 is strictly less than x, is strictly less than 1, is also not countably infinite. Is not countably infinite. Not countably infinite. Okay. So what were we gonna do here? Okay, yeah. So the fact that the open interval from 0 to 1 is not countably infinite now sort of leads us to a new definition here. Okay, we can make this definition here. Here's the definition. Definition. Okay, so an infinite set, a set X is called uncountable if there is a bijection f that goes from x to the interval 0, 1. Okay. So a set x is uncountable if there is a bijection that goes from x to the interval 0, 1. Okay. So examples of uncountable sets are, of course, what we gave in our, at the beginning of class, or towards the middle, I think. Okay, so we have a plethora of uncountable sets. So R is uncountable. Of course, the open interval from 0 to 1, uh, R squared, uh, the set of 3 by 3 matrices in R, etc. These are all uncountably infinite. Uncountably infinite. Okay. So one thing that I do want to sort of mention here is the following here. So back at the beginning of the class, we talked about what happened to the. Is it down here somewhere? Ah, here we go. Yeah. Okay. So now we know what it means for R to be uncountably infinite, because you can find a bijection from R to the interval 0, 1. Yeah? And then we know what it means to be countably infinite. So one thing that mathematicians have been interested in is on the existence of some set with a cardinality in between the naturals and the real numbers. So we could call this set something like S here. Okay. So is there anything in between countably infinite and uncountably infinite? So in between. In between. Okay, now this is called the continuum hypothesis. Okay, so this is continuum hypothesis. Okay, so it says the following: if S is a set such that it's contained in the naturals, and no, it contains the naturals and is contained in the set of real numbers, then the cardinality of S is either uh, the cardinality of N of the naturals or the cardinality of R. So in other words, the continuum hypothesis asserts that there is nothing in between the cardinality of N and the cardinality of R. Yeah. And there's a nice little section in the textbook that I encourage people to read. It's very interesting. Yeah, called the continuum hypothesis. Okay. So now we're, pretty well acquainted with the basics of cardinality and countability and those things. Okay.